channel. I have posted the link there, and I will send that around after all these. We would like the session to be an interactive session with questions, so you can use the chat feature. And for those perhaps not familiar with Microsoft Teams, the chat box looks like a little quotation box. You can press on that, and then you can type in any questions that you have during the session, and I'll be sure to ask those of the presenter. So we're glad that you're joining us today. If you'd like any more information on AMETEK process instruments, I have listed our website address in the slide here as well as in the chat box, so feel free to refer to that at any point now or after the call. With that, I'm going to turn the session over to Tim Talon, our combustion product manager, who will present today on methane and combustion safety. Thanks.
Thank you, John. Can you hear me? Can you hear me, John?
Yes, Tim, we can.
Okay, perfect. All right, so let's get started. Thank you, everybody. Good morning, good afternoon, good evening, depending on where you are in the world. Thank you for joining us on today's important safety topic, specifically methane measurement for combustion safety. So just to get us started, the purpose of this webinar, as you may understand, is the importance of measuring methane for combustion safety. And specifically in our agenda, we're going to talk about the risk of methane accumulation, review some of the fundamentals of safe combustion and those key measurement points for safe operation. We'll also talk about the causes for fuel accumulation and how we might explain that using the 3 T's of oxidation. And we'll go into a few safety interlocks as well as the catalytic design of the methane detector and go into a little bit more detail on those detectors as well. And as John pointed out, we have time available for questions at the end. So feel free to submit your questions via chat at any time, and we'll get to them at the end. Okay, so why are we here? We are here to talk about safety. You know, safety is on us to understand, and we work together to make sure that we understand safety and design that into our plants and our systems. Combustion equipment inherently has a process risk, and it's our goal to minimize this risk and prevent near misses and disasters. And safety and designing for safety is critical to prevent catastrophic events and ensure that safety and protection of personnel and plant are intact. So let's talk about the most common causes for furnace explosions. According to the NFPA, there's several, and they all revolve around the concept of an accumulation of an explosive mixture. So you could have instances of a momentary loss of flame due to interrupted fuel or air supply. You could have a fuel leakage into an idle burner. You could have unsuccessful light-up attempts that are not followed by proper purging. Or you could have an accumulation of an explosive mixture for other types of reasons. And really that concern of monitoring for an explosive mixture is important in part of our discussion today. As a more recent example, in 2015, there was an end user who had an explosion at their electrostatic precipitator. And going inside the incident report, one of the things in the executive summary was that item number 4, the end user lacked safety instrumentation to detect the flammable hydrocarbons flowing to the equipment. And if we just look at that particular item more closely, the end user lacked the safety instrumentation to detect flammable hydrocarbons. And also the executive summary pointed out that the ability to detect hydrocarbons appears to be an industry-wide problem, in this case for the electrostatic precipitator. So this is something that we're going to talk about today, and the importance of really recognizing detecting, measuring for hydrocarbons and methane measurement. And going further, the incident report actually pointed out that the end user installed carbon monoxide analyzers as the personnel believed that the hydrocarbons would partially combust in the FCC producing carbon monoxide. But what happened was, in the particular instance of being in Safe Park, they did not consider the instance of where hydrocarbons would enter the flue gas without the presence of carbon monoxide, and that's what led to the eventual explosion. So measuring for hydrocarbons and preparing for hydrocarbon measurement is important, and that's part of our discussion. But before we go too deep in that conversation, let's talk about combustion overall. So combustion, just as a brief overview, as you may know, combustion requires 3 things. Combustion requires oxygen, fuel, and heat according to the fire triangle. And incomplete combustion causes what we call combustibles. And if we simplify that picture of the reactions of combustion into two reactions, if we simplify it, the first reaction is really where oxygen and fuel react to first form carbon monoxide and hydrogen, which we call combustibles. And then the second reaction, if enough oxygen is available, that carbon monoxide and hydrogen react to form carbon dioxide and water. And so that measurement of combustibles, incomplete combustion, is typically a result of poor air-to-fuel mixing, changes in the fuel loads, malfunctioning burners, and variable fuels. And so when we think about combustion, we think that really the fire triangle is the starting point. So the relevant combustion measurements include the oxygen measurement for process control and quality and process integrity. The measurement of combustibles is important for safety as well as burner optimization. And the measurement of methane is important for detecting flameout and fuel leaks, for example. And finally, if we think about it in a systematic approach, another relevant measurement would also be flow. So making sure that the analyzer has a sample flow that's representative of the process. So those would be the four measurements that we would propose as being relevant to any combustion process. And when we talk about like a combustion system, stoichiometric combustion is what we call perfect air-to-fuel mixing. So you have the perfect combination of air and fuel to produce the ideal amount of heat transfer. So in this case, you have the perfect amount of methane and oxygen to perform the maximum efficiency of the reaction, generating in this case 23,000 BTUs per pound, maximum efficiency. But in reality, in order to have a margin of safety, we actually use a little bit excess air, excess oxygen for normal operation. What that does is it gives us a buffer, and it's slightly less efficient, 5.7% less efficient compared to the previous stoichiometric conditions. But you generate low levels of combustibles, and we measure those with a combustibles detector, and that's normal for normal operations. But where we become concerned is when there's an oxygen deficiency or a fuel-rich condition. And if the heater is not designed to be in a reducing environment, then this is a dangerous circumstance. So when you have oxygen deficiency, you have too high of fuel and not enough air. And in that case, it creates a very unsafe condition where you generate extremely high amounts of combustibles in the percent level range, and you actually also operate 35% less efficient. So not only is it a massive safety concern, but you're also operating less efficient. And so when it comes to designing for proper operating procedures, we always recommend that you operate excess air and you measure that with a combustible detector, and that's and then if the alternative, running substoichiometric, becomes an unsafe and less efficient condition. So the question is, well, what's the right amount of excess oxygen? And this will kind of get us into the zone of thinking about combustion measurements. Okay, so what's the right amount of excess oxygen? So when we think about excess air losses, so when we think about operating at excess air levels, when we have too much air, we use a little bit more fuel than we need in the system because we have to heat up that extra air for the combustion process. So over time, as you increase the amount of oxygen and increase the amount of air, you have more efficiency losses, which is what this graph represents. Higher efficiency losses due to operating at excess air. When you operate with less air, you also have another efficiency loss of generating combustibles. And at the low ppm levels, at the low ppm levels, you'll see anywhere between 100 and 300 ppm of combustibles in normal operation. But after you get to a certain point, you hit what we call combustibles breakthrough, or carbon monoxide breakthrough, and that's really where the efficiency losses increase substantially, and that's where you have a potential unsafe condition. So for any type of combustion process, we recommend measuring both combustibles and oxygen for finding that not only having a operating set point with the oxygen measurement, but also having an optimum control set point or optimal control point by also measuring with combustibles as well when you overlap those two graphs. So going a little bit further, we talked about oxygen. Oxygen provides that operating set point. Combustibles provide a means of minimizing losses, efficiency losses, so you can become more efficient by measuring combustibles and avoid unsafe conditions with carbon monoxide breakthrough. But what about methane? We've talked a lot about oxygen and combustibles, but what about methane? And so methane provides a means of monitoring for safety during startup. So according to NFPA 86, Chapter 11, on Class A ovens and furnaces, the furnace shall maintain the required safety ventilation that combustible concentration is not to exceed 25% of the lower flammability limit under any circumstances. So by monitoring for methane and hydrocarbon during a startup condition, you can ensure that you're below 25% of the lower flammability limit. And so the methane hydrocarbon detector provides an umbrella measurement, which we'll get into a little bit later, to provide a means of monitoring for unsafe levels during purge and light off cycles. And it operates within a 0 to 5% range and monitors, so that you can alarm at less than 1% of the LFL or less than 1% of methane in the heater to prevent unsafe conditions. Now, when we designed the hydrocarbons and methane detector, when we designed that methane detector, it was originally in order to serve this need within NFPA 86, Chapter 11, to make sure that the heater is always below 25% of the lower flammability limit. And that's really where it began as the perception for startup conditions. But what we've found is that the methane detector has also provided a means for monitoring for other unsafe conditions in operation, not just startup. And so those would be things like loss of flame, fuel leaks, tube leaks, and also any type of accumulation above fuelworks mixture. So let's talk about that for a second. So what are the causes or potential causes for a fired heater being exposed or being prone to a flooding condition where you have a highly fuel-rich condition and your burners may or may not be going on and off with flaming out? So some reasons for that might be large swings in the fire duty of on a regular basis, or significant variances in the fuel heating value of the fuel itself, so the changing in the fuel heating value. There could be something mechanical with the air registers not working properly or having to be manually operated, or a heater that is just naturally air limited, and any type of heater that might have had a flooding instance in the past. Those are some common causes for fire heaters being prone to flooding with some type of fuel accumulation. But let's talk about how can fuel accumulate within a firebox? And so with that, I'd like to propose the 3 T's of oxidation. Earlier in my career, I designed thermal oxidizers, and part of that, thermal oxidizers follow the 3 T's of oxidation: time, temperature, and turbulence. So what do you design for when you design for a combustion system? Well, when you design a combustion system, and not just for a flame, but for a combustion system, the first thing you need to think about is fuel. The fuel needs to be well above the auto ignition temperature to combust or oxidize. Now, if a burner is operating, it's already at temperature. You had the spark. It's already feeding itself in the combustion reaction. But in a fuel out condition, that's something that you have to think about is temperature. The fuel needs to be well above the auto ignition temperature in order to combust and oxidize that fuel. The second thing to consider is time. The fuel needs to have sufficient time at the auto ignition temperature or above the auto ignition temperature in order to fully combust and oxidize within a heater at a burner. And third, almost most importantly, is turbulence. Fuel needs to be well mixed with air in order to fully react. And if you're missing any of these three T's of oxidation, you don't have effective combustion at the burner, and you also don't have effective combustion or thermal oxidation within the heater. So for anything later on that doesn't get burned up, you don't have that thermal oxidation later on within the heater. So let's consider the phases of a flame out, for example. In the first case, you may have a burner that loses its flame or over-injects fuel. In that particular case, the flame out due to the burner air nozzle plugging, for example, maybe there's too little air going to the burner. Or you have leaking fuel due to a degraded burner tip, for example, where you have too much fuel, excess fuel entering the system. And in the case where a flame out exists, what happens is you have a localized temperature that plummets to well below the auto ignition temperature. Now, within a fired heater that's a natural draft heater, this may actually be a bigger concern, but you have a localized cold zone. I mean, the radiant heat might help for a little bit, but over time you start to have this cold zone that appears. And that cold zone is, if it were to be below the auto ignition temperature of methane, you have an instance where you have raw methane entering the heater. And then if there's lack of turbulence, especially in like a natural draft heater, that lack of turbulence, that poor mixing isolates that colder, more dense temperature zone around the burner nozzle and doesn't have any interaction. And in a thermal oxidizer, that would be the case where you have a hot flame in the middle, but insufficient mixing of the cold flue gas or the cold waste around it. So in that case, density definitely plays a role in a thermal oxidizer as much as it would play in a flame out condition. And then those differences in density create this accumulation where raw methane would further be introduced to create and accumulate that cold zone. And the differences in density are what really reduce that turbulence and keep those two zones separate. And as the accumulation starts to interact with neighboring hot zones, that peripheral methane could reach its auto ignition temperature, and it could see the low levels of oxygen in the flue gas surrounding the flame to create partial reactions to and partial reactions causing that puffing sound. So that's really where methane starts to interact with the neighboring flames, and then over time you get this afterburning effect where the neighboring flames extend further. You get stoichiometric flames that extend outward, and that's where you see those instances of very high temperature in the firebox. This is where you start to see the high combustibles reading. You start to see no net oxygen measurement. So the zirconium oxide detector would say 0 oxygen is available because there's no net oxygen in this particular instance. And then also you would hear that persistent puffing as you have those localized partial reactions. So going back to the original question, how can fuel accumulate in a hot firebox, despite what equilibrium may tell you? And it's really when you think about the 3 T's of oxidation. The temperature, if a local zone is below the auto ignition temperature, that's a concern for not having the methane react. 2, in the instance of time, insufficient time above the auto ignition temperature. That's where the peripheral methane would react first, given it has enough time above the auto ignition temperature in the availability of oxygen. And 3, and almost most importantly in a fired heater or any type of combustion system, is turbulence. If there's poor mixing that localizes those cold zones, that's really where an accumulation could very much be a concern. And only later on do you detect only later on do you have those other methods of detection with high combustibles and low oxygen. In a real scenario that we've had in the past is we had an end user who was skeptical of seeing a high methane reading. They had a combustion analyzer, and they were surprised to see a high methane reading. So they contacted their local sales representative to hear their thoughts, and the local sales representative suggested that they prove the reading. If they were concerned about the reading, prove the reading by doing a calibration. And so the analyzer went right to the calibrated values on 0 in span gas, indicating that the reading was legitimate. And so the end user took the reading seriously, proceeded with the proper safety protocol, and only later on found that it was a leaky burner. So combustible measurement aside, oxygen measurement aside, in that particular case, it was the high methane reading that became an indication among the other measurements that provided the early detection for a safety risk. Now, where does this all fit into the overall interlock picture? So according to API 556, second edition, there are multiple interlocks, combustion interlocks that you would have for control. You would have your low oxygen override for the fuel controller. You would have your high combustibles override for the fuel controller. You'd have your high combustible shutdown, and you'd also have a startup controlled shutdown using combustibles or hydrocarbon detection not to exceed 25% of the LEL. So in that particular case, the hydrocarbon detector was the detector that helped provide the early detection for normal operation, in addition for a startup condition. And if you were to think about something like power generation, I have with the arrows indicated where interlocks are at play. So during the purge and light off cycle, of course, you would have the methane detector for that early detection. And then also, you'd have that for the detection prior to the electrostatic precipitator. Anytime there's an electrostatic precipitator, we recommend having a methane detector on the combustion analyzer just as a secondary measurement point, just in case, because a combustible detector will tell you the carbon monoxide and hydrogen readings, but a methane detector will tell you the hydrocarbon and methane present in the fuel, in the flue gas. So we always recommend having a methane detector in addition to a combustible measurement prior to a electrostatic precipitator. For a fired heater, as far as hydrocarbon measurements are concerned, or in interlocks, again, you'd have it for your purge cycle, but you'd also have it in case of a burner flameout or for liquid fuels. So another thing to be conscious of. For an ethylene furnace or an ammonia reformer, again, hydrocarbon measurement during purge and light off, but also for flame out and for fuel liquids. And you would obviously want to have multiple analyzers for monitoring each zone of burners every 30 feet or so, every 9 meters or so. For an industrial steam burner, for an industrial steam boiler, you would measure for purge and light off again, and you'd also measure for high methane for a loss of flame or for a swing in the boiler. So there's always I'm reiterating it just because there's always an instance where a methane measurement would provide additional layer of safety, an early indication of an unsafe condition. Now let's talk about the detectors themselves. So overall, there are two different types of catalytic detectors that we use. There's the RTD detector that we use specifically for combustibles measurement. And then there's also a catalytic bead or hot wire detector that we use as well. And the catalytic bead is one that we can also use for combustibles as well as for methane measurement. But in any case, catalytic detectors use an active and reference measuring element. There's two different elements, and the elements themselves are tuned for a very specific zone of reactivity. And I'll get to what that means in just a second, but that zone of reactivity is important because that's what makes it a combustibles measurement versus a methane measurement. And then the catalytic detectors are calibrated to measure those certain compounds in that reactive zone. So a methane detector would be calibrated to methane, a combustible detector would be calibrated towards carbon monoxide and hydrogen. And then also these catalytic detectors are capable of ppm level measurements and also percent level measurements. So you have that balance of ranges of measurement specificity. Let's talk about the catalytic bead detector because that's really where it's used heavily within methane measurement. So the catalytic beads themselves are very small pellicsters. They're between 5 to 10 ohms, and very small pelistors. And as I said before, there's two beads in parallel. There's an active and one reference bead. And the active bead uses a special platinum coating to give it catalytic properties. And it's the nature of those pelistors, because they're so small and they're resistors, they're naturally self-heated, and they're heated to a particular temperature range. And that's what gives them the characteristics of measuring for that zone of reactivity for combustibles or for methane. And according to the reactive properties of the gases introduced, the flammable gases would oxidize on the active bead on that particular active catalytic surface. And from there, the measurement itself is tailored based off of that heat of reaction. As the methane molecule is catalyzed on top of the catalytic bead, the heat of reaction changes the resistance of the pelistor. And so that resistance change is proportional to concentration. And that's how we're able to use it as a means of measurement. This image that I got over from definitely helps to put together the very small, I mean, these are very small detectors, very small elements, but the overall chemistry that happens on the surface. So as a result of that catalytic property, the catalytic beads provide an umbrella measurement. They're not speciated for a particular compound, if you will, but they're speciated based off of reactive ranges. And you're able to measure any type of gas within that flammable gas range, zone of reactivity. And so those catalytic beads are tuned to that specific reactive zone based off of the pelistor temperature. And we use calibration to refine the readings and to zero in on those, those two different elements to refine the readings. And what happens is the combustion reaction is completed by having gas oxidize the sample on the surface. So the measurement, whenever a measurement's taken, the flue gas has additional oxygen in it, and that available oxygen in the flue gas reacts with the methane to oxidize the sample on the surface of the catalytic bead, and that's what's used to complete the reaction. And because of the pelistor nature, because of that resistor nature, the catalytic beads themselves are self-heated. So they're designed to handle high sulfur conditions because they're already self-heated. They're not prone to, I mean, they're hot enough to handle any type of sulfur dew point, for example. Let's talk about the differences of a catalytic detector, between a combustible detector and a methane detector. As I said, the catalytic detectors are tuned for a specific analyte range and zone of reactivity. So a combustible detector is tuned to measure that reactive zone between carbon monoxide and hydrogen. And we calibrate using carbon monoxide, ppm mixture of carbon monoxide and hydrogen in order to ensure that we have greater sensitivity for that reactive range. And combustible detectors are generally designed for 0 to 2,000 ppm level measurements. Obviously, we can tailor to 0 to 10,000 if you need to, 0 to 1%. But what this allows you to do is it allows you to work within your ppm range and measure for carbon monoxide and hydrogen. Again, the incomplete combustion, the compounds you would see during incomplete combustion. But one caveat is that the combustible detector is not operating hot enough to crack methane. There's no response to methane for a combustible detector because it's not operating hot enough to crack methane. Now, the thing to keep in mind is that a methane detector is specifically designed to crack methane. It operates hot enough, and it provides that 0 to 5% level measurement for the detection of, LFL, lower flammability limit measurements. The thing I want to highlight, though, is that the methane detector responds to all hydrocarbons and fuels according to reactivity. Now, we calibrated, again, the calibration is very important, but calibration for methane means that a 1% mixture of methane gives a 1% reading on the methane detector. But what if you had ethane, for example? Well, if you calibrated it with methane, the methane detector would give a 1% of ethane in air using a methane detector would give a 1.1% reading. That's according to the reactivity of ethane compared to the reactivity of methane. So you would be able to detect ethane in an airstream just as much as you would detect methane. And so I've had questions about, well, what about hydrogen? And so a 1% mixture of hydrogen in air using a methane detector would give you a 0.9% reading in air. So that would 0.9% methane measurement reading, hydrocarbons measurement reading. So you are able to use a methane detector, and how the other fuels are reactive, according to reactivity, you'll also be able to pick up the other hydrocarbons in a fuel, or within the process, for example, too. So one thing I want to highlight is that the WG5 uses a specific housing that's designed for temperature stability of these hot wire catalytic bead detectors. So it has a completely redesigned housing using this block that you see right here, this combustible block. This housing can be used to house both the combustibles and the methane detectors in one block. You can see here on the front side, here's the combustible detector. On the back side, we have the methane detector. And so this combustibles block is designed with a heater built in for precise temperature control of those detector elements. And so we also monitor carefully using RT temperature sensor for tight temperature control to make sure that block is operating at the specified temperature at all times within a plus or minus, very tight plus or minus window. And then you may also notice that it's a pretty big thermal block. It's a pretty big block, and that provides an additional thermal mass for greater stability. So these elements, these detectors are built into this combustible block. That's what we call it, the combustibles block. And it's designed with very tight temperature control so that we make sure that those catalytic beads, those elements are operating at a stable temperature without any external fluctuations. So I know we talked about a lot so far, and we're just about done, but one thing I want to highlight is the importance of 3-in-1 combustion operation monitoring. So when we talk about the fire triangle, when we talk about these reactions of combustion, you use the oxygen measurement for safe operation. There's a net oxygen measurement to determine the amount of excess air present in the flue gas, or excess oxygen in the flue gas. And it also provides that process set point for operation. And you use the combustible detector for fine tuning for 0 to 2000 ppm combustion monitoring and monitoring of combustibles. Now that provides a safety monitoring mechanism for measuring for carbon monoxide breakthrough, as we talked about very early in this presentation, but it also provides a means of optimizing your set point for air to fuel ratio efficiency. But again, where the methane detector really fits in is it provides that extra visibility for higher levels for higher viewpoints of safety monitoring. So for safety critical 0 to 5% level monitoring for things like fuel leaks, for safe light off and startup monitoring, and for tube leaks. So really, when you think about combustion, there's really three modes of measurement that really are important for safety and for operation. And so just to highlight some takeaways, some key takeaways from this presentation that I hope are clear at this point is that you can have a hydrocarbon and fuel leak without the presence of partial combustion, without the presence of carbon monoxide. And methane hydrocarbon measurements provide an essential data point for safe startup and for operation of a flame out, for example. Using the 3 T's of oxidation, I hope you guys realize that the accumulation of raw methane can result from a combination of a localized cold zone that creates a localized density difference, and poor mixing can really exacerbate that. So that's absolutely a reason why you could have raw methane in a furnace, for example. And again, accumulation of a methane and hydrocarbon within a heater can be alerted by various interlocks that we described before. So a high or a high hydrocarbon alert mechanism or interlock. And again, one thing I want to reiterate is that a combustible detector does not operate hot enough to crack methane. You really need a methane detector to crack methane and also to monitor it for other types of hydrocarbons, especially at that high, especially methane, obviously, because you need to operate hot enough for methane, ethane, and those types of hydrocarbons. And then finally, just to reiterate, the methane detector provides that umbrella measurement for detecting hydrocarbons, other fuels, and also hydrogen for that higher level. So with that, I hope this was valuable to you. I hope this gives you a better picture for how methane measurement is important for combustion safety. And with that, I will open it up to questions. So if you could submit your questions via the chat, John will ask them one at a time whenever he gets a chance. So thank you for your time. John, are there any questions in the chat?
Hi, Tim. Yeah, thanks for informative presentation. There are a few that have been submitted as you were speaking along the way, so I'll just try to take them from the top, I guess, and hopefully I pick them all up. One question was, if the methane detector can detect hydrocarbons and hydrogen, do you still need a combustibles detector?
Okay, thanks, John. That's a great question. So I would say yes, and the reason is because the two detectors are designed with very different purposes. As I kind of showed in the 3-in-1 slide, combustibles provides you the ability to monitor for efficiency and safety monitoring by monitoring for carbon monoxide breakthrough, that low ppm level measurement. And that low ppm measurement provides that means of monitoring for incomplete combustion, CO breakthrough, not enough air at the burner. Now, the methane detector, as I mentioned before, the methane detector was originally designed for use during startup and light-off cycles. And it was to effectively be an a lower flammability limit detector for those startup conditions. But over time, what we found is that the methane detector also complements normal operation by monitoring for flame outs, fuel leaks, and potential process tube leaks. And so the two measurements are very important, and they're also very different. So I would say you certainly need. I would say that there's a value for having both a methane detector and also a combustible detector for that ppm level visibility and for that percent level visibility. So thank you.
Great,
Any
thanks,
other
Tim.
questions?
Yeah, another one came in, Tim, asking if you could provide some detail on how the methane detector is calibrated.
Okay, that's a good question. So believe it or not, it's actually very similar to how we calibrate the combustible detector with zeroed span gas. But what we recommend for calibrating with methane is actually we recommend using a gas mixture of 2% methane, 2% methane with 8 to 10% oxygen and a balance of nitrogen. And it would be its own separate cycle for calibration, but it'd be very similar to how you calibrate for combustibles, and you'd use the same zero gas ratio. Good question. Yeah, that's how we would calibrate for methane.
Okay. Another one specific to, I think, one of our instruments anyway, but question on what are the temperature differences for CO and hydrogen sensor and the methane sensor in the WGD5 CM?
So that's a great question. I'd have to check with one of our technology scientists, but as far as the specific numbers, I can't remember offhand. But what I can say is that it's sufficiently different for the standpoint of that carbon monoxide. I mean, obviously the whole system has flame arresters to begin with on the front end, on the inlet and outlet of any type of measurement. So you don't have to worry about any type of concern there for the temperatures of the catalytic beads themselves. But what I can tell you is that the combustibles measurement, operates at the temperature to catalyze carbon monoxide and hydrogen, and the methane detector operates hot enough to crack methane without being, astronomically hot, but hot enough to crack methane. And we've used it for, we've designed these well over 30 years ago, and really have refined the technology to serve for these critical safety measurements. But I would say that obviously the combustible measurement is obviously is cooler than the methane temperature.
Great, thanks, Tim. A couple more as they keep coming in. Appreciate the questions from the audience. Another question for you, Tim, is whereabouts in a fired heater would a combustion analyzer for methane detection be installed for optimized performance?
Thank you, John. That's a great question. I would say that this kind of aligns with API 556 second edition, but you would first install your combustion analyzer to be at the exit of the radiant section. You want to minimize any potential tramp error to the combustion analyzer itself. But that being said, if you also want to maximize the monitoring of the installation, you would also consider placing the combustion analyzer to be above or as close as possible to the location of the burner that you would light during startup. So if that makes any sense, the burner that you would light during startup would be one place that you could put the combustion analyzer to ensure that you have some safe operation during the quickest path to the greatest visibility during startup for a potential flame out during or fuel leaks during startup. That being said, I would also recommend putting a combustion analyzer prior to with methane measurement prior to a electrostatic precipitator, just to make sure that you have all of your safety ducks in the row, if you will, checked off before going to the electrostatic precipitator. So I hope that answers your question, but above at the exit of the radiant section, just so that there's enough time for the combustion to not to be too close into the flame itself, so that you're at the incomplete combustion range, but just as API 556 would recommend, at the exit of the radiant section. Hope that answers your question. Hey, John, you might be on mute.
Well, thanks, Tim, for the answer there. That's great. There's another question that's come in regarding some debate going on overall in the industry, but question is, have we been ever able to validate the existence of hydrogen in the unburnt fuel?
Existence of hydrogen in unburnt fuel? Just taking a moment to think about that question. So that's an interesting question. I think, obviously, when we talk about
clarification, Tim, was CO and hydrogen, I think probably versus CO2, maybe, or versus CO. Sorry, CO and hydrogen versus CO versus CO.
The question makes sense. The question makes sense. So I think so obviously, I simplified the combustion reaction to be two separate reactions. I mean, there's obviously you could obviously break it down into the specific mechanisms for carbon monoxide, specific mechanisms for hydrogen. So what I can say is that, especially if you're using refinery fuel gas that has fuel that has very high amounts of hydrogen, there's even greater chance of detecting hydrogen as part of incomplete combustion with a refinery fuel gas, especially a refinery fuel gas that has up to 70% hydrogen. It's kind of an interesting question, because hydrogen does have high kinetics to react with any available oxygen, but also in equilibrium, when you do the equilibrium reactions for combustion, for example, equilibrium would say that there's a sufficient amount of hydrogen to be concerned about in a substoichiometric operation, for example. So while I feel like every heater is different, so it's very difficult to say that there's a proving out point of hydrogen, the presence of hydrogen, I can say that, from the standpoint of equilibrium, there's absolutely hydrogen present. From the standpoint of kinetics, that hydrogen may react faster to any available oxygen, but in that case, you would also there's still a need to monitor for hydrogen, any potential hydrogen present, especially if you're using refinery fuel gas that would have high hydrogen, for example, where there's even less fuel and much more hydrogen available in the fuel gas, where you would want to obviously use a combustible detector for measuring and monitoring hydrogen. So I hope that answers your question around the presence of hydrogen in the form of incomplete combustion and combustibles measurement.
A couple more questions have come in, Tim. One is, by adding the methane detector, is the SIL rating still applicable?
That's a great question. That's an interesting question. So what I can say is that the SIL rating is actually for the oxygen measurement at this time. So right now the oxygen measurement, it has the SIL rating, but by adding a combustibles measurement and a methane measurement, it does not void any SIL rating. So if you have oxygen and you want to design your system for SIL and add combustibles and methane, it's still a SIL rated analyzer. So,
okay.
Yep, that's a good question.
Thanks, Tim. Another one has come in. Would the hydrogen be detected by both the CO detector and the methane detector?
So so the short answer is yeah, but you got to talk about the ppm level versus the percent level range. Again, with a combustible detector, you'll detect the ppm level range. So that would be the first alert for high hydrogen. And then should that persist to percent level, the hydrocarbon detector would pick up on that. Absolutely. So hydrogen would be detected in both instances.
Okay. And then another one, possibly, I guess, comparing some different technologies. Is there an advantage to measuring combustibles versus only CO by TDL?
Right. So this is where we go back to the umbrella measurement. And I know we're talking about combustibles, but I really extend this to methane and hydrocarbons. So the advantage of using a combustible detector is that zone of reactivity. So there are sub-mechanisms for within any combustion process, within any combustion reaction that we don't talk about. Like there's phases of aldehydes, phases of as those hydrocarbons get broken down. Now the simplest reaction is with methane, as it has a shorter path to getting to become carbon monoxide. But it's really the ability to also monitor for hydrogen. It's the ability to monitor for any intermediate combustion species, if you will. And it's that zone of reactivity that provides you that extra flexibility. Same with measuring for methane measurement. Like it's not just a methane measurement; it's an umbrella measurement for measuring other hydrocarbons as well. And so, if you're using again refinery fuel gas that has high hydrogen, I would definitely advise a combustible detector because you're not only measuring for incomplete combustion, but you're also measuring for combustibles. You're also measuring for hydrogen. And if you have high refinery fuel gas with high hydrogen, then you'd want extra visibility for that, for any unsafe condition. So I'd say that there are certain circumstances where it would absolutely be valuable to have a combustibles measurement outside of a traditional carbon monoxide measurement.
Great, Tim.
Great question.
That was the last question that came in on the chat. Tim, appreciate your time today to do the presentation and also thank everyone for attending today's webinar. As I mentioned at the beginning, the webinar recording will be available within about 24 hours, and that link will be sent out. If you need any more information, please feel free to visit amatechpi.com, review any information on the combustible products, combustion and oxygen products. And again, thank you all for attending today's webinar, and have a good rest of your day. Thank you.